uh, to what class is it? Comp 330. It's nice to see you all. So this is tutorial 8, in case you were interested by the tutorial's number, and the date is hopefully right. So today we will be doing more exercises about decidability, and also doing some NP sort of complete exercises as well. I just have to warn you, usually I rehearse these tutorials before I give them, so then typically they're a bit more comprehensible. Today I didn't have time to do that because I got locked out of my office. So please bear with me in case I say anything that's very strange or incomprehensible. Um, okay, so everyone, the projector's working, everyone seems happy. Okay, so let's get started, right? So what I'm gonna start with today is decidability decision problems. Decidability decision problems, which have to do specifically with Turing machines, because there's very likely a question about this on your assignment. So I thought it might be useful to do a question like that as well here. Okay, so we're going to start off by looking at just an exercise that asks us to determine whether a decision problem is decidable or not. So that's what the question of this is That's what the question of this exercise is. Thank you. So is the following decision problem decidable? And the decision problem here is going to be called AP-330. And AP-330 says or asks, given a Turing machine M, so, like a sort of infinite tape Turing machine, the one we've seen in class, deterministic and so on, does M accept any string? Sounds familiar. Within 330 steps, hence AP-330, right? So essentially, you're given, like, imagine you're trying to design an algorithm to decide this problem. So what your algorithm is supposed to be given is a Turing machine, right? You're given a Turing machine, and you want to design an algorithm which looks at your Turing machine and checks, is there any string, right? Any string over sigma star. So we can assume sigma is not empty. Is there any string over sigma star where when you give it to the Turing machine, it runs for at most 330 steps, and at some point before hitting the 331st step, the Turing machine halts and accepts the string. Okay, this is the algorithm for which we want to. This is the problem for which we want to design an algorithm for. Yes, thank you. So what I'm going to do is I'm going to give you like 2 minutes to think about it. My phone's in my locked out office, so I will use my laptop's timer. Really great when you get locked out. Great feeling. Um, okay, so I'll give you like 2 minutes to try this out. No, not 0 minutes. Starting now. So think about it. It's fairly similar to a question in the assignment. So thinking about it will not be a waste of time, which is good, right? You don't want to waste time. Hello. Hello, hello. All right. So what do we think? Is this decidable? Undecidable? You cannot decide whether it's decidable or undecidable? What a great joke. We have no opinions. No opinions? You think it's decidable? Okay. Well, let's keep things short. Why do you think it's decidable? Like high level idea.
With like stability and the machine,
Hmm.
and because we only need to check 330 steps.
Mm-hmm.
So if it's
Okay. Let's stick with let's stick with this idea, right? Let's stick with this idea. So one person is saying it's decidable. Okay. And this person, sorry, what's your name? Anne?
Yeah.
Okay. So Anne is saying that you can decide this because you have sort of a finite number of steps to run a Turing machine M on a string array, right? I think I agree with this intuition. So I think what you're sort of talking about is an algorithm that might look like this, right? So it's decidable. Let's try to design a decision procedure based on this intuition. So the algorithm for AP-330, it might be something like this. So in this case, the algorithm, the input to the algorithm is a Turing machine, right? So on input M, so M is a Turing machine, right? What are you going to do? Well, you're just going to simulate the Turing machine M on all of the strings in sigma star, right? So, well, let's actually do that. So for W in sigma star, right, run M on W for 330 steps, right? If M accepts by the 330th step, right? Then the Turing machine, this sort of algorithm, so this meta Turing machine, right? It should accept. Okay, seems reasonable, right? Seems reasonable. If the answer to the decision problem is yes, this is definitely going to work, right? So if the answer to the decision problem is yes, there is a string, right? Yes, I know. There is a string in sigma star for which when you give it to the Turing machine and you run it for 330 steps, at some point it's going to halt within those 330 steps and accept. This is definitely going to check that, right? So if you have like if you have sort of a certificate or a witness or a guess that you want to check, this is definitely going to do that, right? But what if, right, this is very possible, what if the answer to the decision problem is no, right? Then what happens? Now you can say what you want to say.
That's not what I was going to say.
Oh, oh, that's not what you're going to say. Okay.
Like the language, like you have sigma star.
Sigma star is infinite. Right. You can't test everything because you're just going to keep waiting, right? So what if the answer to this question is no, right? Then, well, you have to check, right? So this procedure is telling you, well, go through each string, right? Run each string for 330 steps. And then if at some point one of the strings leads to an accept within 330 steps, then you accept. But what if none of the strings lead to that? Then your Turing machine is essentially just going to be, your algorithm, sorry, is going to be stuck in this for loop, right? It's going to keep going through each of the strings, then it's going to check if this if statement is true. It's not going to be true. So it's just going to continue to the next string. Right? Right? Okay, good. Excellent. So that was a very good intuition, right? This does not work. This does not work. Put this here. This does not work because if the answer is no, then algorithm, let's call this algorithm one loops forever. Okay. But that's a good start. That's a good start. Do you want to? Yeah?
Can we go like
Yeah. Maybe. Yeah. I think I know what you're going to say. Okay.
like if we draw like I guess the states and the transitions.
Yes. Yes. Okay. Let me. You're taking my punchline. But yes, I think you might be onto something. Okay. So I'm gonna talk about it in a slightly more abstract way, and then I think I know what you're trying to say. So yeah, one more question, and then we get to something. Yes. It's not even exponential. Exponential would be great. I would love exponential here. It's infinite, right? Infinite runtime. Yeah, sigma star is infinite, right? Right? Sigma star is infinite. Well, sigma, I say, is not empty. So as soon as you have a non-empty language and you apply sigma star to it, then unless it just has epsilon, but if it has like a non-empty string in it and you apply sigma star, boom, it becomes infinite. No, a string is never of infinite length, at least not in 330. I'm saying if you have some language which has like a few strings in it and you apply sigma star, right, then the resulting language is infinite. So if you're not convinced about that, I can just show you after. Okay. Okay. So essentially this doesn't work because we're sort of trying all the strings, right? But maybe we don't have to try all the strings, right? Maybe we don't have to try all the strings because consider this this observation or this statement. Now, I'm going to phrase it as a question. So if no string of length at most n gets accepted within n steps, is it possible for any string of length strictly greater than n to be accepted in n steps? Okay, this is my question to you. Maybe it's a rhetorical question. Okay. So I'm asking, I have a string. I know that, like, imagine n is 330. Maybe that's a good idea. So if n is 330, right? And I'm telling you that no string up to length 330 gets accepted within 330 steps, right? And then I somehow tell you that in the same number of steps, in 330 steps, your machine is able to accept a string of length 331. Does that seem right? No, right? That doesn't seem right. Why doesn't it seem right? Because, imagine, right? I have my string W, right? My string W is of length n, right? And I run, right? So I run M on W for n steps, right? And I'm telling you that all the strings of like at most n don't get accepted, right? So like in the worst case, right? In the worst case, what could the Turing machine be doing? It could be sort of hard coding all of the strings of length at most n, right? So it hard codes all the strings of length 1, 2, 3, up to 330. And so it has like branches, right? It has a branch for length 1. Then it has a branch, 2 more branches for length 2, right? And all of these are leading to rejects, right? So you're not accepting, right? Either they're looping or they're rejecting, right? So whenever you're running M on W for n steps, this W always gets rejected, right? And then I tell you, well, take the same string W and then stick sigma onto it, right? Just stick sigma onto it. So now it has length n plus 1. But run it, right? Run it for the same number of steps. This is the key thing. So if I run M on W for n steps, right? The same number of steps as before, right? Then it's impossible in this case that the Turing machine will accept a string W sigma because it only has 330 steps, right? And in those 330 steps, all it could do, like in the worst case, if it was really, really silly, it could read through all of the strings sort of one letter at a time, and then finish at the 330th step at the 330th letter, right? That's sort of the worst case, right? But now if I tell you, well, stick a letter onto that, but I don't give you an extra step, right? So I don't give you an extra step. So I end up here, right, at step 330. Maybe, right, maybe if I had an extra step, I would accept the string, but I don't have an extra step, right? I only have 330. So if in the worst case, I'm sort of running through the entire string, right, and I stop here, right, then because I didn't accept this string, it's impossible for me to say, well, I know that there's a sigma ahead, but I'm not going to sort of do a computation and I'm going to accept, right? That's not, you can't sort of magically guess, oh, there's probably something that's going to lead to an accept there, right? So that's why the answer in this case, right, is no, this is impossible. Was that the question? If no string, is it possible? No, this is not possible. And the intuition is because you have the same compute budget, right? So you have the same compute budget, but with a longer string. You have the same compute budget with a longer string, but you know that sort of all of the previous shorter strings with the same compute budget didn't get accepted. So if I just give you more string, then this is not going to help you, right? Within the same budget, right? Is this intuition clear? Okay, Jonathan.
What if there was an already existing string that was length more than n, but was accepted by the tuning machine by n steps? For example, let's say there was a
Right. Well, that's a different question. But yes. So I think, so your question is, imagine I had a string of length 335 and it got accepted,
Yeah.
right? Then what can we say about strings of shorter length? Is that the question? Maybe? That's a good question. Okay.
There was another string x, for example, that was accepted in the 330 steps. But then doesn't that mean that it's possible?
Well, the if here is no strings of length at most 330 get accepted, right? If at least one string of length 330 gets accepted, then you can't say anything about strings of length greater than 330. Because maybe that string got accepted because it was sort of looping forever, or maybe it got hard-coded, right? Maybe it's sort of in a loop of accepting anything, right? So if you give it any string that looks like this of a certain length, then you immediately go to an accept. That's possible, right? In which case you would accept all other strings that had that as a substring, right? Or you could have, the Turing machine could be something like, if the string looks like A, B, something like this, right? Then accept, right? Otherwise, reject, right? So if one string, like if at least one string gets accepted by the Turing machine in like 330 steps, so because this is length 330, the Turing machine actually has to check that this is the correct string, right? Then you can't say anything about the remaining strings, right? At least nothing very broad. Is that clear? Okay. More or less? Okay. Okay. You can ask me about it later after. Yes. That's what I assumed you were asking. You were gonna ask. Anyways, what a waste of. Oh. I'm not sure you want to do that. So the question is, well, why can't you just like open up the Turing machine and just sort of look for a path, right? Well, why can't you do that for the halting problem? Right? Why can't I just be like, oh, there's a while true, so it loops forever? You can do that. That's a heuristic, right? But the heuristic, what undecidability theory tells us is that the heuristic is going to cover some cases, but never all cases, right? So it might be that you're checking the code of the Turing machine and you cover a lot of cases, but definitely not all. Yeah, good question. Okay, so now with this factoid in mind, how can we take this and convert it into an algorithm which doesn't loop forever? So the algorithm is going to be very simple. So this is going to be algorithm 2, which is also going to take on input Turing machine M. So what it's going to do is, in this case, I'm going to be a bit lazy and just run all strings of length at most 330 for 330 steps each, right? Each. And then if one, right? So if one gets accepted then this algorithm 2 accepts, right? So accepts the Turing machine. Otherwise, right? Otherwise, it rejects, right? And in this case, my algorithm has no chance of like a false negative because of the logic I just sort of stated here, right? So then this algorithm works out. And so the takeaway, right? So you might be asking, why are we doing this? So the takeaway is if you have this kind of condition, right? If you have some kind of condition where you know that if no strings get accepted under a certain condition, then no other string after that is also going to get accepted, then that sort of condition can be useful when you're trying to answer decision problems that have sort of an at least in it. So in this case, I'm asking, is there at least one string, right? Then the reason why this this fact was useful is because I'm asking for at least one string that gets accepted within 330 steps, not all of the strings, right? Okay. So if it was all of the strings, then that's also hard. So the takeaway is use a fact about if no string gets accepted under X, then no other longer string will get accepted under X. Okay, so this is a aggressive hint. I had a TA once tell me, I'm giving you an aggressive hint, which is very strange. How can a hint be? Anyways, this is a hint that should help you for one of the questions in assignment 4. Okay. Any questions about this? Yeah?
Assuming that you need to stop, we can only process, like the program only process one bit of this. Right, like if you have a
Yeah.
Oh.
Yeah. We're assuming that, yeah, so that's a good question. The assumption in this question, and the assumption you can make for Turing machines that we see in the class is to process like one letter in a string, you need one step.
Is it always true that if there's a question that
you can apply this assumption for assignment 4 Turing machines, yes.
anything? Yeah.
And exam, sure. Exam. Yeah. Okay, good. Yes. Is this no, this is certainly, well, it's a bit hard to qualify the running time in terms of the size of the Turing machine. Because if you want to define it, if you want to define the running time, you have to define it in terms of the input you're given. So it's a bit hard for me to tell you. Let me get back to you on that in terms of the running time. It's a bit strange to. Anyways, I'll get back to you on that. It's definitely finite, right? Yeah. But if it depending on sigma, this step is gonna take more. Like if sigma was just A, then you would have to run only on 331 strings, yes. Right, because epsilon as well for 330 steps. Yeah, because the input you're getting is the Turing machine, it's hard for me at the moment off the top of my head to tell you how you would qualify the running time, because how do you define what the size of a Turing machine is? Is it number of states? Maybe it's number of states. That's interesting. I guess maybe in terms of number of states, you might be able to say something. Yeah. Yes, last question. Can we modify this Turing machine? But why? Why do you want to modify the Turing machine? For the assignment? No modification of Turing machines in assignment. Unless you're explicitly asked to modify Turing machines, which I don't think you are. Okay. Great, excellent. So hopefully this is helpful for one of the questions in assignment 4. I have another similar question, but because it's similar, I think I might just post the notes. Yeah, so I have another, I'll just write, I have another exercise that is similar, which I will post. Similar exercise post on my courses. Okay, so let's now move on to the PCP problem. So the PCP problem, so let's just recall the post-correspondence problem, right? So what is the post-correspondence problem? This is another undecidable problem, right? Where in this case, we sort of stopped dealing with Turing machines, and we're now just dealing with domino tiles, basically, right? So we have a set of, let's say, 3 strings, let's say A, B, A, B, A, B, and then A, B, A, and A, B, A. Right, so these are like my domino tiles, in case you've ever played dominoes. And the goal is to see whether you can use any number of tiles and arrange them in such a way where the top tile, like when you read it from left to right, is the same as the bottom tile, right? So is there, okay, so just to review, does there seem like there's a solution to this instance of the PCP problem? So I'll give you like 30 seconds to think about it, which I need a timer to do that. I guess you can't see it anymore now. Yeah, I'll just count my head. Okay. So what do we think? People are still figuring it out? Okay. So let's just because this isn't like that interesting. Let's see. Well, I definitely can't start with this tile, right? Because if I started with this tile, then I would have an A and then a B, so that would be bad. So then that means I can either start with this tile or this tile, just because I don't want to waste that much time. I have a good feeling that I have to start with this tile. So let's do that. A, B, A. Okay. So now, what tile can I use? Well, I can't use this tile again because then this AA would go here and I wouldn't match. I also can't use this tile because then I would have A and that would match. So I have to use the first one. So A, B, A, and B, A, B. Then at this point, I again sort of have, at this point, it's ambiguous whether I should use this one or this one. I just know for a fact that I should use the red one, so let me just do that. But in a sort of real world scenario where you don't know the answer to the question, you would have to just sort of trial and error, right? See if it works out. And now at this point, it looks like a pretty good bet is to use this tile because I'll have an A here and then A, B, A at the bottom. So then I get a nice sequence of domino tiles, okay? So then in this case, the answer to the PCP problem, so the 2 PCP with the instance of the problem S is yes. But of course, this is not always true, right? You have some S's where you don't have, the answer is no, right? Imagine if you have tiles where the top is always shorter than the bottom, then there's no winning in that case, right? So it turns out, you saw this in the lecture 17 and 18. So from lecture 17 and 18, you saw that actually, even though it seems like a very toy problem, the post-correspondence problem is undecidable. So there does not exist an algorithm which, given an arbitrary S, can decide in finite time whether there's a solution to S or not, right? And how did you actually prove this? I'm not going to redo it, of course, but I think it's important to just remind you of what the sort of reduction was. So you have this PCP problem, right? But all of the problems that we've been dealing with in terms of undecidability have been with Turing machines, right? So how do you sort of connect domino tiles and Turing machines, right? Well, what you sort of did in the lecture is you sort of said, well, why don't we reduce the acceptance problem to the post-correspondence problem, right? How, right? By connecting instantaneous configurations and transitions in the Turing machines to sort of having to select one particular domino tile, right? So essentially the general argument, I'm skipping the fact that you modified the PCP problem. I'm just giving you the high-level idea. We sort of said something like, M accepts W, right? If and only if you can, from the starting instantaneous configuration, you can get in some finite number of steps, any number of steps, to an accept state, right? This is just true by definition. And then what we did is we said, well, let's take the Turing machine, right? Let's take the Turing machine with all its states and its transition functions. And what else does the Turing machine have? Its tape alphabet and its input alphabet. Let's take all of that and encode all of that logic within an instance of the post-correspondence problem, right? So you had something like sort of you created S. So then S was created as a function of M and W, right? So for instance, one thing that you did is you sort of said, well, let's start with a domino tile that looks like the hash at the top and then the hash Q naught W at the bottom, right? And then you had other things. And what the reasoning behind this was you were forcing a solver to the post-correspondence problem to start with this tile, right? And so by virtue of starting with this tile, starting at the sort of starting instantaneous configuration of the Turing machine. And then the solution, the way your PCP solver was solving the instance of that problem was actually by sort of reconstructing the transitions in the Turing machine, right? So that's essentially what you were doing at a high level perspective. So when I taught this, I actually did the proof and it was extremely brutal. So I'm very happy I didn't have to do it this time. No, it's also fun though. So let me just write. So S was created. All right. So I wrote that. If and only if S is equal to this, and the solution to the post-correspondence problem is something like, you get the top and the bottom being the same, where that's just a sort of simulation of the instantaneous configuration. So maybe you get Q1, you get an A and a B, Y here. Then you do this up until something like X, Q, A, Y. Okay. So it's very hard for you to just get what exactly was done by me speaking in 5 minutes, but the high level idea is hopefully understood. And it's just that, you want to simulate a Turing machine accepting a string by making that simulation being the same as if you were to solve an instance of the post-correspondence problem, right? So you have to sort of create S such that when you're solving it, that's the solution. The solution is a simulation of M on W, running M on W. Okay. So hopefully that's more or less clear. Yeah, more or less. Okay. Okay. So now why is this interesting? Well, it's inherently interesting for you because it's on the assignment. But it's also just interesting because you can actually show that other undecidable problems like a context-free grammar being ambiguous, those are undecidable by reducing from the post-correspondence problem. So it's much easier when you have that in your back pocket. But for the purposes of this tutorial, the reason why I wanted to talk about this is because even though the post-correspondence problem is undecidable, there are variants. Well, let me not talk about it that way, although I might have given the answer away. There are other variants of the post-correspondence problem, right? So let's look at another variant. So this variant is called PCPn, and PCPn is given a set of tiles S. Is there a PCP solution which uses at most n, oh, m, okay, because it's important, m tiles, right, with repetition. Okay. So this is the decision problem. Okay. This is the decision problem. So I want you to think of, this is actually useful to think about if you weren't listening to what I just said before. Let me give you 1 minute or 2 minutes. No, 1 minute. Enough. 1 minute to think about this. Oh, clarifying question. Yes.
That like you have a set of 5 tiles, then we get to use 3 kinds of tiles.
No, using
Like
how many the total number of tiles you can use is up to n.
the length, like the length.
I wouldn't say the length of your solution. I would say, like, imagine you have 10 tiles. All together, all of those tiles together, you can use them. Wait, oh, I see. The total number of tiles that you use is n.
So the maximum length of your
I feel like it's as a function of. Yes, as a function of. Yeah.
Are we using, for example, let's say it's 10 times, so we use 3 and we repeat those 300 times. We could do that, or like the M.
If you have 100 tiles and I tell you m is 5, then you can only use all of the tiles all together. Oh, I see. This is like ambiguous in terms of English. Okay, let's write it mathematically, then it won't be ambiguous. Suppose you have n tiles. So let's just stop the timer, given that, oh, the timer didn't even start. That's great. So suppose you have n tiles, right? So you have like T1, T2, Tn, right? And let's say N1 is the number of times you use tile 1, right? N2 is the number of times you use tile 2. Up till n sub n, that's the number of tiles you use tile n, right? Then what PCPn is saying, or I guess it should be PCPm. Oh boy. What PCPm is saying is that the sum, right, of this is at most m. Now that's what this is saying. Okay. All right, now let's start the time. And I need to disable these. What am I getting? All right. But what are we thinking? Say someone else other than Yusuf. Yes. It's decidable. Excellent. Very good. Why is it decidable? Very good. You read my mind. There's only a finite number of ways of setting up the tiles, right? So just list all of those ways, check all of them. And if one of them gives you a solution, you accept. Otherwise, you say, no, sorry. It's a no, right? Very good. So this is decidable. Decidable. Why? You can just brute force it. Brute force it, right? So a very pseudocode algorithm, you know, like let's call this algorithm 3. So on input S and M, right? Just list, right? So list all possible solutions, right? And then check each one, right? So check if the top is equal, right? We can do string matching. You just do equals equals in Python. And if one, right? So if one is a solution, we accept, right? Otherwise, and this otherwise is sort of finite, right? Otherwise, we reject. Reject or say no, right? Good, very good. Now, what is the runtime of this? Size of S, right? So not great, right? So the runtime is something like, yeah, I would agree with something like this. It's probably even worse than this. Because, I mean, if you do it really, really dumbly, then you can probably do it even worse because you sort of, anyways, yes, it's exponential. Let me just not get ahead of myself. Sorry. So the runtime is something like exponential. So this is exponential. And now my question to you is, well, that's not good. Can we do any better? Can we do, oh, we can? Can we do any better? Well, can we, really? Oh,
But like, not like.
like essentially, do you think there's a polynomial time?
Oh,
Okay, so this is my segue to the NP-complete part of the tutorial. So can we do better? Well, really what we're asking, right, is we're just asking is sort of, is it in P versus, well, yeah, is it in P versus, really what we're asking is it polynomial time or NP hard, right? So non-polynomial time and no better, right? So the best we can do is we assume we have like a non-deterministic Turing machine, which sort of guesses the correct solution somehow magically, and then checks that it's right? So this is the question I'm actually asking, right? So is it in P or is it actually NP-complete, right? So to answer this question, let me just quickly recall what it means for something to be NP hard or NP complete. So really, let me just say, or NP complete. So recall NPC for NP complete, not non-playable character. So what do we mean by NP complete, right? So the first thing, right, the first thing that it means for a problem. So if a decision problem A is NP complete, then the first thing is that the decision problem is in NP, right? So A is in NP, right? What does that mean, right? What does that mean is if I have an answer, if I have not an answer, if I have a guess to A, I can check in polynomial time whether the guess is right or not. right? So this is what it means for something to be NP, is if I give you a guess, you can check in polynomial time, right? But that's like most problems are in NP, right? I mean, take like sorting. I think I got a sorted list. Let me just check that it's sorted. I just checked that it's sorted, right? In ON, right? In this question, right? In this question, I can also sort of check the answer in P time, right? So yeah. Yeah, so it's no. What if the answer to PCP is no? Then you can't check that it's no, because you have to keep running forever.
Yeah, but it's like if you.
No.
If you have a guess, like.
We're gonna get sidetracked. Let's talk about this later. So, but I see what you're saying. Let's talk about it after. It's a very good question, but we're gonna get tangentially sidetracked. So that's what it means for something to be an NP is I give you a like guess to it, and you can check it in polynomial time. Okay, and then the other thing for something to be NP-complete in is that every problem, so every problem in NP can be reduced to A, right? So in other words, so you take every problem in NP, so maybe like B, C, D, whatever. All of those problems are at most as difficult as your problem A, right? So that's what it means for something to be an NP-complete. It has to, like the problem is an NP, so you can check in polynomial time. And it's at least as hard as all other problems in NP, right? So usually we just say that that means that it's NP hard. Okay. So that's the sort of quick recall of the definition of this thing. Now, let's actually come back to the example. So I wanted to first recall the definition and then come back to the example. So is PCPm, so it turns out, let me just give you the answer. PCPm is NP-complete, right? So we can check this because it turns out it is in P, right? So how can we check that PCPm is in P? Like how do I check? Yeah, that it's an NP. Yeah.
Just take guesses of like potential solution.
Yeah, so you just check. Yeah, exactly. So you just well, no, I'm telling you, I have a guess to the so I'm telling you, I'm giving you a guess to the solution of the PCPm problem, right? And I want to see if I can check it in polynomial time, right? So the easy way to do that is just, well, to check if the top string is equal to the bottom string, right? Right, so that's what I'll do. So I just check. So if I'm given a guess to the PCPm problem, right? So meaning I'm given like a solution. I say I use these tiles at most this time, and this is the top, and then this is the bottom. Then I just check, right? I check if the top is equal to the bottom, right? And I could do this in polynomial, right? Okay, so now the harder part is to show that this problem is in NP hard. Now it's actually going to be quite difficult for me to explain this to you, just because I haven't practiced this explanation yet. But let's see if I can do it. Okay. So what I'm gonna do, typically what you do to show that something is NP hard, this is the easy thing to do, is you just take some problem in NP, which you know is NP complete, and you reduce from it, okay? Now, this is not exactly the approach that we want you to take in assignment 4, in particular for the PCP problem. What we want you to do is we want you to take an arbitrary instance, that's an NP, and reduce from that instance to the PCP problem you're given. Right? This is what we want you to do. So that sounds challenging, and it's definitely challenging to explain. Okay, so let's try. Let's try. How can I do this? How can I take an arbitrary problem in NP and reduce it to the PCPm problem? Okay, so well, let's just take a problem. So take a problem A in NP, right? So I have some problem A in NP. Now, what does it mean for A to be an NP? That means that there exists a non-deterministic Turing machine M such that M decides A, right? And in particular, it decides A, right, in polynomial time, right? So it can sort of, the way it does this is it guesses. Guessing takes 0 time, or very close to 0 time. And then the checking is the thing that takes the polynomial time. So, right, then the Turing machine M on an input of size n runs in P of n, where this is a polynomial. Right, so something of the form n to the k plus n to the k minus 1 and so on, right? So it's a polynomial, right? Okay. So far so good. I'm just stating the premise, okay? Now, what I need to do, right? What I need to do now is I need to somehow take this problem, right? So what I want to show is that I can take this problem A, which is just an arbitrary problem in NP, and reduce it in polynomial time. So reduce it in polynomial time to PCPm. Okay. So how do I do this? Like, remember the sketch for this is I can sort of solve, to show this, I want to show that if I can solve the PCPm problem, then I can solve the A problem, right? So what I want to do is I want to create an A solver from the PCPm solver. Okay, so this is going to say yes or no. And then this is going to be the input of A, right? So the input of A, and then I'm going to have to modify it. So I have a some kind of input modifier, which then goes, so it somehow creates an instance of the PCPm problem. So an instance of the PCPm problem is a set of domino tiles and some integer m. Yeah, some integer m, right? So how can I do this? Well, the trick is going to be the sort of intuition that I gave you at the beginning in the from the undecidability reduction from AP to PCP, right? So in that mapping reduction, what I did is I took the transitions, the sort of working mechanisms of a Turing machine, and I converted that into domino tiles. So I'm just going to do the same thing, right? So you're going to see why this is going to be useful. So I'm going to convert M and its transitions to a set of domino tiles. Let's call this SM. And so this conversion, right? This conversion, it's probably not that hard, hopefully, to see that it's polynomial in time, right? Because I have the size of my Turing machine is sort of bounded by its number of states. And I'm not creating sort of an exponential number of tiles based on the size of my Turing machine. It's just sort of like, each state becomes a tile. Yeah, each state gets converted to something like a hashtag, the state, and then what's on the left and the right of the state, and so on, right? So something like that is polynomial. So this is polynomial in time. It's a hand-wavy argument because if I give you the precise argument, we'd be here all day. But try to convince yourself that it is a polynomial time sort of convention. Okay. And then, right, so then what I'm going to notice, right, is I'll notice, right, so SM, right, SM is created. This is created such that a solver would need to simulate the computation of the Turing machine on some input, on its input, right? Okay. And so what you need to notice then is a transition, right? So a transition, so a single sort of computational step, a transition for M. So one step in M's computation requires a finite number. So it requires a finite number of tiles to represent it. Right, because like, remember, if I have a transition like X, Q, sigma, Y gives you X, gamma, PY, right? And this is sort of represented as a tiles of dominoes. So I have something like X, Q, sigma, Y here, right? Then to get from here, right, to get from here to here, something like X, Q, sigma, Y, and then X. So then this is going to be here, Q, sigma, Y, X, gamma, PY, right? So to get from this sort of partial solution of S sub M, to this partial solution of S sub N, it's going to take a finite number of tiles, right? So that's sort of the hint of how you're going to get the bound, basically. So this requires maybe like K tiles, right? So this requires maybe K tiles to sort of represent this, right? Okay, so then, well then consider the transition for the computation of M, which requires the maximum number of tiles, right? So you can know this, you don't actually have to simulate the machine. You can just look at the machine's architecture and you can say, well, it's going to be fairly complicated for me to simulate going from state Q to state P when the string I'm reading is A, because I have to sort of, if it's non-deterministic, I have to sort of loop through the Q and then maybe use an epsilon transition, something like that, right? So I have to go through a lot of steps to go from this state to this other state, right? So basically, there's some number of computations, right? That or there's some number of tiles that are required to transition from one state to the other state for all of the Turing machine states. And now I just take the one that requires the maximum number of tiles, right? So let's call this K prime, right? Then what I know, right? What I know is given an input to given an input to this decision problem A, the Turing machine M, which the non-deterministic Turing machine M, which decides A, right? That's going to run for Pn steps, right? But then what's the maximum number of domino tiles I'm going to need to use to simulate that? Well, I know that the maximum number of domino tiles to simulate one transition is K prime, right? So let's just imagine that it was the worst case all the time for each single step. Then I just say, well, take K prime and multiply it by Pn, because Pn is the number of steps I take, right? So each step, right, one step in your Turing machine is going to take K prime domino tiles in your solver of the PCP problem. Okay. So then I'm going to use that. And so given an input to A of size n, I'm going to convert M to Sm, right? And that's polynomial time. And then pass Sm and then K prime times P of n to the PCPm solver, right? And then the solver, right? The solver, I'm sort of simplifying a little bit, but the solver can use at most K prime times Pn steps, K prime times Pn tiles. So then it has enough sort of total number of tiles to simulate the computation of M on W. And the sort of tiles have been designed such that if M on W, if M accepts W in Pn steps, then that's going to be reflected in the solution. Then there's going to be a solution to the PCPm solver. And if there's no way of getting from the starting configuration to an accepting configuration, then that's going to be reflected in the PCP solver saying no. Okay. So then the way we sort of design this is then the PCPm solver will say yes, if and only if M has a successful, that's how you write successful computation on the input of size n. Okay. And then so that means that we've taken an arbitrary instance, an arbitrary problem in NP, right? So we've taken an arbitrary problem in NP and we've reduced it to the PCPm problem, right? So this means, right? So therefore, PCPm is NP hard. And so by 1 plus 2, we get that PCPm is NP-complete. And so the answer to my original question, can we do any better than exponential, is then no, because the best we could do is because the problem is NP-complete. Okay. Man, that was brutal. The reason why I did this example, despite it being extremely hard to explain and slightly unintuitive, is because it's probably pretty important for the assignment. So I'm sorry if the explanation was terrible, but hopefully the notes will make up for that. Okay. Yes. What's 1 plus 2? Oh, as in, I thought for a second you were, anyways. As in, like, we've shown this. We've shown that PCPm is in NP, right? So it's in NP. And we've also shown that it's NP hard, right? So when you show these two things, it means that the problem is NP complete. So NP complete just means that if you were to solve this problem, then you could solve every other problem in NP. Okay. Okay. Yes. Yes. The guessing you can just assume takes like 0.1 time step. Like the guessing is just, I mean, you can't guess in real life, right? So you just say, oh, it just guesses for free, right? Yeah. Good. Okay. Okay. Okay, so this was brutal. So in general, the good news, right? So then the good news is in general, we don't have to go through this excruciatingly difficult process of taking an arbitrary instance of in NP and then reducing it to the problem you have, because we actually have this very useful theorem, which is if this is the set of all problems, all decision problems which are in NP, then it was shown for us by a guy, I think his name was something Cook, who went to the University of Toronto. He showed that all problems reduce in polynomial time to the SAT problem, right? So the SAT problem is, given a sort of formula, a logical formula, is it satisfiable, right? Is this logical formula satisfiable? And at the same time, we also have this result that the SAT problem reduces to 3-SAT, right? Which is when you have sort of logical formulas in conjunctive normal forms where you have terms that are sort of length of 3 expressions, right? And the reason why that's helpful is because a lot of the work has been done for us in sort of taking the 3-SAT problem and reducing it to other problems like the vertex cover problem, which I think, did you do that in class? Okay, so the vertex cover problem and other problems like Hamiltonian cycle, which I think is in your assignment. That's also NP-complete, and you can sort of polynomial time reduce it from 3-SAT. So the nice thing about that is now you can take just one problem, right? You can take just one problem that's NP-complete, right? One problem that's incomplete, NP-complete, which has been shown through maybe a 3-SAT to that problem reduction, and you can reduce from that problem, right? So you can reduce from that particular problem rather than just, you start with almost no assumption, which is just that your problem is an NP. Okay. So why is that nice? Oh, I guess I should maybe write this. Okay, so in reality, right, to show A is NP-complete, what you actually have to do is, the first thing you have to do is show that it's an NP. And the second thing you have to do is you have to show that there is a problem which you already know is NP-complete because someone has already proved it for you. Whoops. And you show that this problem, right, this problem, polynomial time reduces to your problem of interest A. Okay. So that's much easier, right? Because now you're actually dealing with a concrete problem and you just have to sort of take an instance of that problem and convert it in such a way that it looks like an instance of this problem, right? So I'll just remind you, what does this mean? What does the second part mean? It just means that I can create a solver for B, right, by using a solver for A. Right, so I have an instance of B, and I modify the instance of B. So I sub B just means instance of B. And this the only restriction is that the modification has to be polynomial time. So in polynomial time. And then you modify it such that you get an instance of the problem A. And you design it such that when the solver says yes, then the answer to your original problem was yes. And when your solver says no, the answer to your original problem was no, right? So you design the modification such that the answer so this is just answer of the instance of the problem B is yes, if and only if the answer to the instance of the problem A, which was modified. So this is sort of designed as a function of this, is also yes. Okay. Good, clear? Okay. So that's much easier, right? Because you just have to deal with like one specific instance modification instead of one messy arbitrary modification. Okay. So let's do with the 8 minutes that I have left. Hopefully there's not another class. Maybe I can run a bit over. Let's do a few examples of this. So the classic thing to do when you do sort of, oops. Oh no, that's not good. Maybe we only do have 8 minutes. So the classic thing to do in terms of like examples and exercises is to sort of use graph theory examples. These are sort of the most common ones when you do NP-complete exercises. So let's do an example where we want to show that the independent set problem is NP-complete by reducing it from the K clique problem. I guess it's K independent set. Okay. So maybe not everyone knows what these two problems are. So I'll just write IS for short for independent set and CLQ for short for clique. So let's just take some graph, right? So some graph. So the right. So let's start with the K clique problem. Asks, does this graph G, right? So does this graph G, does G have a clique of size K? So what's a clique? It's just a subgraph of your graph G, which is complete, right? Where all of the vertices are connected to each other, right? So for instance, if I take this graph G and I ask, is there a clique of size 4? 4? Yeah, thank you. Is there a clique of size 4? Then the answer would be yes, because I can take, this subgraph and this subgraph, right? So this subgraph here, each of the vertices is connected to all the others, right? So this vertex is connected to these three. This one is connected to these three and so on, right? So this is a solution to the 4 clique problem. Okay, excellent. What is the independent set problem? So the independent set problem is, again, suppose I have a graph. This is another graph, G. An independent set is a subgraph of G where none of the vertices are connected, right? So in this case, if I ask, is there an independent set of size 3? Then the answer again is yes, because this subgraph, so this is a solution to the 3 independent set problem. Okay, is this clear so far? Okay, this is just a setup. Now, what I want to do, it turns out you can sort of do a reduction from vertex cover to K clique. So you can actually show that K clique is NP-complete, right? And so then once you show that K clique is NP-complete, it's typically very standard to then show that independent set is NP-complete because the sort of modification is fairly simple, right? So now what I want to do is I want to show, what did I say? K independent set is NP-complete using the fact that K clique is NP-complete, right? Well, if I want to show, first of all, if I want to show that K independent set is NP-complete, the first thing I have to show is that this problem is in NP, right? But that's fairly easy to check, right? So how do I check if, how do I show that K independent set is in NP? Well, suppose I have a graph, right? So imagine I have this one, right? And I have a guess, right? A guess to the solution of the K independent set problem. What is that guess? The guess is, well, it's just a subgraph, which I claim is independent, right? Which you have no connections to it. So then I take that guess and I give it to my checker. And my checker just has to go through each of the vertices and check, if I'm using like an array in terms of the data structure for the vertex, it doesn't matter. But if I'm using an array, I can just check that from this vertex, I don't point to any other vertex. Right?
Group action, one of the circle, one of the triangle. The circle still is.
Yes, yes, yes. Yeah, independent from each other. Yes, yes, yes. Thank you. Yes. Oh, if you have something like this, right, then is this thing still an independent set? Right? The answer is yes, because independent set means you're independent within the subgraph. Yeah. Okay, good question. Yes. Okay. So then is it cool if I just put a check mark and I don't write the actual procedure for like it's an NP because I can just, if I'm given some subgraph, which I'm claiming is independent, then I can just check that each vertex is not connected to any of the other vertexes in the subgraph, right? Okay. So then the actual more difficult part is the reduction, although it's not that, not much more complicated. So if I know that, so I know, I guess there's not a class. Cool. I know that K-clique is NP-complete. So what I need to do is I need to do K-clique polynomial time reduces to, whoops, K independent set. Right? So what I need to do then is I'm going to be sketching this box a few more times. If I have a K independent set solver, right, which is answering yes or no, right, then I should be able to create a K-clique solver. Right? So what does a K-clique solver do? It takes some graph G and some number K. And then when you give it to the K-clique solver, it should tell you yes if there's a K-clique and no otherwise, right? But to create this K-clique solver using my K independent set solver, I need to somehow modify. So I need to create an instance modifier, which takes GK and converts it to an instance of the independent set problem. But the instance of the independent set problem is also a graph, so G prime, and also a natural number K prime, right? Where when you give that to the solver, then it tells you, yes, there's a independent set, independent set of size K prime, or no, there isn't, right? So is the setup clear? The setup is clear? Okay, so we don't have time for me to give you time, if that made sense. So I'm just going to tell you that there's a very nice sort of lemma that I'm going to leverage for this problem, which I'm not even going to have time to prove, sadly. But the lemma is the following. If I have a graph G, which has a clique of size K, right? Then this is true if and only if, yeah, that's wrong. If and only if the complement of the graph G has a independent set of size K as well. Yes, right? Why? Because like imagine I have the complete graph K4, right? So this is my complete graph K4, right? So it has a clique of size 4, right? Now take the complement, right? So taking the complement of the graph just means that where there is an edge, remove that edge, and where there isn't an edge, add that edge. Well, in this case, you have all the edges for this graph. So if you take the complement, right, then that's just the graph that has 4 vertices, right? And so I have these, I have this sort of clique where all the vertices are connected. So if I do the complement, then all the vertices in that same subgraph will not be connected, right? So then this thing is like an if and only if. And that's essentially how the proof goes, but I of course don't have time to do that. Okay, so then what does that mean in terms of the instance modifier, right? What is the instance modification going to be? Invert all the edges, so meaning that G prime is going to be what? Yeah, right. Well, the complement of G, right? So G complement. And what is K prime going to be? K, it's K, right? And so this works by this lemma, right? So this works because now, if GK, so the instance GK has answer yes, right? Then by this lemma, it means that this other graph G prime K prime has answer yes. So G prime K prime has answer yes. And if, on the other hand, well, we can do the contrapositive. So if the answer to this is also yes, right? Then by the same logic, because this is an if and only if, the answer to the original problem will also be yes, right? So what I know then, what I know is that if I have an instance of my K-clique problem, and the answer to that problem is yes, then my instance modifier preserves this yes, right? And if the answer to this problem is no, then my instance modifier also preserves a no. And this modification is polynomial in time, right? Which tells me that I need only a polynomial amount of time to solve the K-clique problem with the independent set solver, which means, right? Which means if you sort of just think of this in terms of an exam, that, well, if I can solve the K independent set problem, then I can solve the K-clique problem. So that means that the K independent set problem is harder, right, than the K-clique problem, right? Because if I can use this, if I can use the strategy for solving this to solve this problem, then, well, that means I can solve my problem and also this problem, right? So that means that this problem is harder than this, or at least as difficult. Yeah, okay. Yeah,
One part is
is it? Sorry? No, it's the runtime of the modification would probably be something like the number of vertices times the number of edges, something like that. Because you go, right? If you're, yeah, okay. Right? Okay. Okay, cool. I have another one, but it doesn't look like there's a class. So I can do it or I can stop. But this one is more relevant to the assignment. So keep going. Okay. If you want to leave, that's fine. It's recorded. So I'll give you a second to decide. Huh? Okay. Yeah. Do you think? Yeah. Yeah. Is it recording? Yes. Okay. Sorry, Yusuf. Sorry, John. Okay. So, this other example is a bit more related to the assignment because it has to do with like paths in a graph, which is sort of directly connected to sort of Hamiltonian paths. So in this other example, we want to show, yeah, no problem. We want to show that the longest path problem is NP-complete. Okay. So what is the longest path problem, first of all? So, oh, is there a class? So the longest path problem is, let's find out. Given a graph G, right? Does G have a simple path? So a path where no vertex gets repeated. So a simple path of at least K edges. Right. And the reason why it's called the longest path problem is because you can use the longest path problem to actually find the longest, like to actually find the size of the longest path, right? You just go through each K one by one, and at some point you're going to have the answer to sort of you know, the answer to Gn is going to be yes, and the answer to Gn plus 1 is going to be no. So then the longest path is of length n, right? That's kind of why it's called that. Okay. So we want to show longest path is in NP-complete. So yeah, see, we will do this by leveraging the fact that the Hamiltonian path problem is NP-complete. It's NP-complete because you're going to show that in the assignment. So what is the Hamiltonian path problem, though? So the Hamiltonian path problem is given a graph G. In this case, we're assuming it's undirected. So we're assuming the graph is undirected. And two vertices UV in V. Does G have a Hamiltonian path from U to V? Right? And so a Hamiltonian path is, you know, if I have a graph G and I have a vertex U and a vertex V, a Hamiltonian path is a path which goes through each of the vertices, right? Exactly once. Doesn't exactly once. It doesn't repeat any vertices. And, you know, in this case, goes from U to V, right? So all the vertices get visited exactly once, and you go from U to V, right? That's a Hamiltonian path, right? So you go from U to V, each vertex once. Okay, so we want to show that LP is NP-complete, right? So how do we do that? We have to first show, we have to show two things. We have to show that LP is in NP, and we have to show that LP is NP hard. Is it clear that, how do I show that LP is in NP? No guess? Oh yeah, sorry.
Given a path, there is
Yeah. So given a path K, given a path P, you check that it has length at least K, and you also just check that it's simple, so no edges are repeated. So that's probably, you know, if you're being super silly, K squared, right? Something like, or length of the path P squared in terms of runtime, right? Because, you know, you're going through the path and you're checking that each vertex is not before, right? And then you're just counting it to see that it's equal to K, right? Or greater or equal to K. Okay, cool. So you check that P is simple, okay, plus of length at least K by just traversing it, by traversing the path. Okay, great. So now the more tricky part is to show that it's NP hard. And so we're going to leverage the fact that the Hamiltonian path problem is NP hard or is NP complete. So what we want to do is we want to do the Ham path problem reduces to the LP problem. Okay. So what we want to do, again, like I said, I'm drawing this box many times just because I think it's helpful. We want to create a solver for the Ham path problem using a solver for the LP problem, right? And so we're going to do that, right? So we're going to do that by given an instance to the Ham path problem. So an instance of the Ham path problem is G, a graph G, and then two vertices. We're going to take that and we're going to give it to our instance modifier. And the instance modifier in polynomial time should convert this, right, to an instance of the LP problem. An instance of the LP problem is a graph and a natural number K, right? So it's a graph G prime and a natural number K, right? I'm not telling you what K and G prime are yet, but this is at least what the setup is. Okay, so whenever you don't really know how to start a reduction, the best thing to do is just to sort of not modify or modify as few things as possible and see why things are going wrong. Okay. So for instance, suppose I have a graph G, right? And I have two vertices U and V. I want to know if there's a Hamiltonian path from U to V, right? So let me just not modify G, right? Let me just not modify G. So let's just say that G prime is G. And in terms of the longest path, let me just assume, I don't know, let me just assume that if I have a Hamiltonian path, right, then it covers each of the vertices, right? So if I have V vertices, right? So imagine I have three vertices, then the length of the Hamiltonian path must be from the length of my Hamiltonian path must be something like if I have three vertices of length 2, right? So it has to be the number of vertices minus 1. Right? So the Ham path,
Should you
sorry.
versus you
No, we're assuming they're distinct. So that's a good point. We're assuming this instance of the Ham path problem is U is different from V. Yeah, that's what we're assuming. Okay. Otherwise, this strategy is still doable, but you have to take the same vertex and kind of split it, right? Yeah. So I mean, we're assuming U and V are different, but if they were the same, right, you could check that and you would say, well, just add an extra vertex and sort of split these two, right? So this strategy will still work, okay? So, but what I wanted to just say is, if I have a Hamiltonian path in G, the Hamiltonian path is going to cover each vertex once and exactly once, right? So then the length, if I have a path which covers each of my vertices, like imagine I have 5 vertices, then my path is going to have length 4, right? So the length of the path is going to be V minus 1, okay? So let's just try that, right? Let's just try G prime is G and K prime is V minus 1. Okay. And let's just think whether this is going to work or not, okay? So if I do have a Hamiltonian path from, yeah. If I do have a Hamiltonian path from U to V, right, then the longest path is definitely going to be, is definitely going to be of length V minus 1, right? I can't have a longer path, which is simple, right? Because the restriction here is that the longest path should be a simple path, right? So no vertices should be repeated. So if I have a Hamiltonian path, right, from U to V, then it must be that the longest path is of length V minus 1. So I have a yes goes to a yes in that direction, but do I have a yes goes to yes in the other direction? That's what I have to check, right? So yes goes to yes in this direction is okay. But what about yes goes to yes here, right? So suppose in my graph, I have a path of length V minus 1, right? Does that necessarily mean I have a Hamiltonian path from U to V? No, right? Because I can have something like, the longest path could be something like, I start here, then I go here, then I go here, then I go here, right? But that's not a Hamiltonian path from U to V. That's a Hamiltonian path where U and V are part of the path, of course, but they don't start and end at U and V, right? So this is not good. This is not okay. Okay, so, well, at least that's good news. At least I know that this sort of direction was good. So basically, what I need to do is I need to just slightly modify G prime and K prime such that if I have a longest path, then I must have had a Hamiltonian path from U to V, right? Does anyone have an idea of how I might be able to do that? Yes.
I part of the idea would be to take unity out G prime,
Mm.
and then look to see if you have a path that includes everything else. But then you somehow
But then you
make
stop.
sure that you would connect the right.
Right. Okay, so this is a very common strategy. It's a bit of a pitfall because what you're essentially saying, like your solution, it's a good idea, but in your solution, what you're sort of doing is you're assuming you can solve the Hamiltonian path already. Because you're saying, well, take U and V, take it out and see if I have a path from the rest of the graph. But there you're already sort of making an assumption that you could check if there was a Hamiltonian path in there, right? So you sort of have to force it in a way that if you have that the longest path must be the Hamiltonian path. That's kind of what you want to do instead, right? And so how can I do this? So a very simple modification to my graph would be, well, something very similar to what you just said. Let's add two new vertices, U prime and V prime, right? And let's connect U prime to, whoops, let's connect U prime to U, right? And let's connect V prime to V, right? So now G prime is, G union U prime, V prime, plus its edges, right? And now K prime, right? I've added two vertices, right? So now my K prime is going to be V minus 1 plus 2, right? So it's going to be V plus 1, right? How am I doing on power? Okay, right? So it's going to be V plus 1, okay? So now let's see what happens, right? Okay, so I'm in a completely different space, but let's ignore that fact. And let's just say what we need to do at this point, now that we've created the instance modification where G prime is now the graph G union these two extra vertices, plus of course their edges, and K prime is the length of V, so the number of vertices I started with in G, plus 1 because of this sort of minus 1 plus 2 thing, right? Now I want to show the correctness of this reduction. So I first want to show that if I have a yes to the instance of the Hamiltonian path, which as a reminder is GUV, right? It's not GU prime V prime, it's GUV. So if my answer to my instance GUV is yes, then I have to argue that my answer to my LP problem, where the instance is now G prime this guy and then K prime this guy, this should also be yes, right? Well, if I have a Hamiltonian path, right, from U to V, then it also means that I have a Hamiltonian path from U prime to V. Why? Because, I just start from U prime, I go to U, and then I use the existing Hamiltonian path, and then from V, I go to V prime, right? So, so if I have a Hamiltonian path, right, in GUV, then I also have one in G prime UV. And that Hamiltonian path is of length V minus 1 plus 2, like we just sort of explained, which is greater than or equal to K prime. So I do have a yes instance for my initial problem. So this is yes. Then I also have a yes to this modified problem. So that's great. And that was sort of what we sort of expected just because it was working in the initial, more naive modification. Now, do we also fix this problem of a yes on the right? So my answer to my LP problem is this also a yes answer to my left, right? So an answer to the hand path problem. Well, so now suppose I have, so there should be K prime, but now suppose I have that G prime and K prime, right? The answer to the LP problem is yes, i.e. this graph G with U prime and V prime does have a path of at least V plus 1, right? Well, if this path, right, is simple, which it has to be because the longest path problem stipulates that the longest path has to be a simple path, right? Then there are only V vertices in my initial graph G, right? And so the longest path in V is at most v minus 1, right? So if my longest path is actually of length at least v plus 1, right? That's actually the maximum. But if it's of length v plus 1, then that must mean that it also includes this edge and this edge, because these go to two new vertices that weren't initially in my graph, right? So that means that if the answer to this problem is yes, then because of the way I constructed G prime, I know what the solution must be. I know that the solution will be, the longest path will be u prime to u, and then some path u to v, which is of length v minus 1, and then an extra edge here that goes to v prime. But then what does that mean? That means necessarily that I have a hand path from u to v. It's namely the one that was part of this longest path, right? And so I also have that a yes from my answer to my LP problem is a yes to my answer of my hand path. Okay, and that sort of shows, or hopefully convinces you that this correction was, this instance modification was the right one. And this shows, right, so then therefore, LP is NP hard. And so since LP is in NP and NP hard, this implies that it is NP complete, i.e., if we were to solve somehow the LP problem, if we had a polynomial time algorithm that solved the LP problem, then all other problems in NP would actually be polynomial time, and we would have that P would be equal to NP, which would be pretty extraordinary. Okay, so that does it for this tutorial. I also made a few corrections in the PDF here, so if you're still watching, just try to skim through the PDF again. And I had seen a few sort of typos that I made, and so I've just fixed them in red. Okay. So I hope this was helpful, and I'll see you next time.